Hello everyone, welcome to Tech Talk with Ritesh. I am Ritesh and today we are diving into the fascinating world of generative AI. It's in talk everywhere over social media, in the organizations. If you are into technical, you will hear this term again and again, Gen AI. Okay, so whether you are a tech enthusiast, student, or just curious about how machine can create art, text, and even music, you are in the right place. In this tutorial, we are going to explore how Gen AI or generative AI works and understand its key concepts. So, what can you expect from this tutorial? First, we will do the introduction to Gen AI. We will start with the very basics. What is Gen AI? Why it is so exciting? We will see the key models. We will break down the popular models like GANs, VAEs, diffusion models, LLMs models, etc. How they work, what are they, etc. We will learn about them. We'll see some real world applications from realistic images to generating text and beyond that we will explore. So we are ready for this journey and you want to unlock the secret of Gen AI. So make sure to hit the like button, subscribe the channel, yeah, so that you don't miss out any of your future tech explorations. So without any further delay, let's get started and dive into the amazing world of Gen AI. All right, let's start. So Gen AI, and the full form is Generative AI, and since the term AI is added to it, of course it is coming, the roots are there in AI, which is artificial intelligence. So first let's understand what is artificial intelligence. Artificial intelligence is made up of two words, artificial and intelligence. So what artificial is, created by humans, not something that happens naturally, of course. So that is called artificial. And intelligence is something, the ability to understand things, learn from experiences and solve problems. That is what make you smart. So now combining this, something which is created by human, okay, and machine can perform, and so that the machines will work smartly, that is called artificial intelligence. Okay, artificial intelligence refers to the field of computer science dedicated to creating systems capable of performing tasks that would normally require human intelligence. This includes tasks such as learning, reasoning, problem solving, perception, and language understanding. Or in simple words, it is like giving computers and machines the ability to think, learn, and make decisions, almost like how humans do. It is like teaching a computer to be smart and make choices on its own. Now let's see the fun example. So it's like we ask Siri or Google Assistant schedules your meetings, sets reminders, and answer questions by learning from your preferences. So once they know what are your preferences, because they have already learned from previous historical data, because you are interacting with these bots frequently. So now they learn, and after that learning period, now they are able to assist you. Now how I have designed this whole course is that first we will learn all the key concepts, all the key terminologies we have in AI, and then we will go to Gen AI, and then we will see all the terminologies, the key concepts in Gen AI. The first thing is, after artificial intelligence, what is machine learning or ML? So machine learning is a subset of AI focused on the development of algorithms that enable computers to learn from and make predictions or decisions based on data. So basically machine will learn based on some data, okay, and then do some tasks. So how this learning happens of the in the ML. So basically the training, we train the ML first, the training, the machine models, we first train them, and there are various type of learnings. How do we train the model? One is supervised learning, which is training a model on labeled data to make predictions or classify data. So for example, a spam filter trained on emails labeled as spam or not spam. So for example, if any email is labeled as spam, it will go to spam folder, or if it is not spam, it will go to a primary inbox. So that is kind of a supervised learning. Second type of learning is unsupervised learning. So training a model on unlabeled data to identify patterns or group similar data points. So for example, grouping customers based on purchasing behavior without predefined categories. So we're just grouping the customers, for example, returning customer or the existing customer, new customer, right? So we are grouping all those customer type. Next one is reinforcement learning, which is training an agent to make decisions by rewarding it for desirable action and penalizing it for undesirable ones. So for example, training a robot to navigate a maze by rewarding it for reaching the goal. Now let's see a fun example. So let's imagine that we have a pizza ordering robot named PizzaBot. So initial orders, at first PizzaBot takes random pizza orders because there is no data, there is no learning at all, right? It's just a new bot with blank, with no idea of your preferences. So first time it is interacting with you, right? So that interaction will happen, it will ask for orders, you will give the order, you will tell your preferences, etc. Learning from feedback. Each time you order, PizzaBot notes what topping you like or dislike and how often you choose certain pizzas, etc. Right? So now it learned and then it stores that information, because next time when you interact with the same bot, it will see, okay, yeah, the last time this person was not liking chili flakes, etc. Right? So it won't give you that advice. Better recommendations over time. PizzaBot starts recommending pizzas you are more likely to enjoy, like spicy, pepperoni, surprise, if it notices you love spicy food, or vice versa, right? So it is learning based on so first it is having interactions, and based on this interaction or the experiences or whatever information we are feeding this model, it is learning, and on basis of that learning it is providing recommendations. Next concept is deep learning. What is deep learning? Let's see that. So deep learning is a subset of machine learning involving neural networks, and we'll see what is neural network with many layers, and we call it as deep neural network. These models are capable of automatically learning feature representations from raw data, and applications would be, for example, image recognition, natural language processing, speech recognition, etc. So machine learning is one thing, and one step ahead is deep learning, right, where we will have the neural network and with many layers, and we also call them as deep neural networks. Next concept is natural language processing, or NLP. So NLP is a field of AI focused on the interaction between computers and human language. That is why it says natural language processing. It involves tasks such as understanding, interpreting, and generating human language, sentiment analysis, language translation, chatbots, Google Translate for translating text from one language to another. These all are the examples, and we use this natural language processing so often with our daily routine. So for example, if you have maybe Siri, Google Nest, Amazon Echo, Alexa, etc., right? So you can do something, for example, scheduling some meetings, right, or morning wake up calls, or daily briefing. I mean, whatever you want to do, your schedule, etc. You can just train those assistants, and they can guide you or they can help you. Now let's see the fun example, and we do it on daily basis. So for example, we do WhatsApping or any of the messaging app we use, right? Imagine we are texting with a friend, and as we type, our phone texting app suggests word and corrects spelling mistakes based on what we are typing. For example, if we are typing, there is a typo, right, and it automatically gives suggestions also. Sometimes when we do WhatsApp messaging, etc., we see that it automatically tries to correct, or it will at least give you that option that this is the correct one, and we can just tap on it and then we can fix it. Here NLP helps your texting app suggest and correct words to make typing faster and more accurate. So we are already using this feature. Now next concept is computer vision. Let's see what it is. Computer vision is a field of AI that enables machines to interpret and make decisions based on visual data from the world. Object detection, facial recognition, autonomous vehicles, facial recognition system used for unlocking smartphones. These all are the applications. They are here since long. So it means it is nothing but artificial intelligence. So it's there in the system since long. Now we have almost seen so many topics related to AI. So the question is, where is generative AI? Where it fits in the whole concept behind this artificial intelligence, etc. Where is generative AI or Gen AI? Gen AI is a specific subset within the broader field of AI, machine learning and deep learning, and it focuses on generating new data. So wherever you guys see, there is a term which should be highlighted. I have highlighted in yellow. So Gen AI focuses on generating new data samples. That is a key to remember, that mimic the characteristics of a given data set. So remember, always remember, the data which is generated, it's a new. It's not there in the system at all. Whatever you are getting is a fresh, newly generated data. Okay, it will just mimic the characteristics of whatever input you have provided. So it will generate the data, but it will always be new. It creates new content or data from existing data, right? So for example, if you get any data from any of the Gen AI application, so for example ChatGPT, don't think that it is there somewhere in the system and it is just based on what you are inputting. It will see, okay, there is a match, 2-3 words are matching, and then it will just copy the whole Word document data and then paste it. No, it's not like that. The data is generated with smartness, and that data, the phrases are totally new, that content is new. The question arises, what is the need of this? Why we even need that? So Gen AI aims to produce novel data that is similar in structure and content to the data it was trained on. So it produces novel data. One thing to remember, this can include images, text, audio, or even complex simulations. It can be used to aid in creative processes by generating ideas, artwork, or designs, and there are limitless we can think of. So it will just produce novel data. That is the keyword we need to remember. It's always new and novel. Now let's see the key points of generative AI. Generative models are trained on large data sets to learn the underlying patterns and structure. So when I'm saying large, it means really huge data. So for example, if I want to train maybe a system, so it is not just like 1 MB data, 2 MB data. We are talking about data in GBs. So first we need to train the models, the generative models, and after they learn, then only they are able to serve. They are able to provide you that. They are able to generate the that fake data or that novel data. A model trained on images of cats can generate new images of cats that do not exist. So it means it's always new. Output of generative data model is synthetic because of course it is artificially created. Capture the essence of the data. So whatever input we provide, it captures the essence of that raw data, which allows to generate new similar instances. Okay, now it says capture the essence of the data which we are training on. So it will just capture the essence of that data, and when we are inputting something, then it will use that data to generate a new similar instances. Now here we have this term called generative models, and the question will be what are those models? What is the use of them? Let's see that. A generative model is a type of machine learning model. Learns to generate new data samples that are similar to a given training data set. So first we feed in, okay, with the training data set, right? And generative model learned using those data set, and then using those that data through which this model is trained, it generates new data samples. Now let's understand with one fun example. Imagine a quilt maker who has seen thousands of quilt patterns, check boxes, the squares, the rounds, etc. If you order a quilt with a mix of geometric and floral patterns, the quilt maker combines these styles to create a unique, vibrant design that has not been seen before. That was the idea. The quilt maker generates new quilt designs by mixing familiar patterns and elements, producing creative and original patterns based on previous designs. So what quilt maker has done? The previous historical learning he has, because he has made so many quilts, now he is using that learning, and now with that learning he is generating a new quilt design, mixing into all those patterns, and this is a unique design which has never been created before. That is the idea. Okay, it's a fun thing. So let's learn neurobiology before we move on to further of topics. Okay, the question is, what is neuron? A neuron, and this is human, and within human brain, a neuron is a fundamental cell type in the brain and nervous system responsible for transmitting information throughout the body. So this image is not that much complex, but if we really see those images provided by medical stuff, neurobiology system, etc., this is neuro. Basically, this is a very complex system. Okay, okay, even I was like, okay, that was too much biology, and let's get back to neural network. So neuron, we understand that it's a cell type in human brain, right? Now what will be neural network in AI then? A neural network is a machine learning technique that teaches computers to process data like the human brain. Okay, so what we are trying to mimic whatever we have in human brain, because the key concept is intelligence. Intelligence comes from, of course, brain. So we just trying to mimic brain with artificial brain. That is like giving brain to computers. Okay, so we will create a neural network in machines, that is artificial neural network. Neural networks are made up of interconnected nodes or artificial neurons that resemble the neurons and synapses in the brain. So we are just trying to make the same thing whatever we have in human brain. So let's see how do they work. Neural networks are inspired by the human brain, where neurons send electrical signal to each other to process information. So for example, we touch something, it's cold, it's hot, etc. We see something, that information is also goes back to the neuron system in the brain, right? We feel something emotional, we are getting excited, angry, etc. All those things, right, connected to through brain to our neuron system. In a neural network, artificial neurons or nodes work together to solve problem. Likewise in our brain. So the question is how they are trained, because if for human, for example, if you want to teach something to a kid, we just the kid learn from the environment. Parents also teach the kid, right? But how these artificial neurons will be trained? Neural networks are trained with large data sets to adapt and improve their performance. So one thing for sure, that if you want to teach any model, it requires large data sets. It's in GBs or even more, right? So that, I mean, whatever information we want to teach, whether it's a generic information or a specific information, we have to feed in that information to that system, and then only it will learn. Okay, neural networks are trained with large data sets to adapt and improve their performance. They can identify patterns and make decisions based on data, and can adapt to changing output patterns. So artificial neurons, no, we are not going to make human cells. Like I said, artificial neurons, like we are just trying to mimic the same thing whatever we have in human brain in the machines. Artificial neurons are inspired by biological neurons but are simplified and adapted to work within computational models. It receives input, processes it through a mathematical function, and trust me, those are very complex functions, and produces an output that can be passed to other neurons in the network. So I mean, one neuron will receive the information, will pass it to other neurons, and they are all interconnected. So that is how the information is flowing from one side to another side, right? And okay, this is the pictorial representation how neurons or this whole neural network work, right? So the information is flowing inside, input 1 2 3 so on, there are so many input, and this is the input layer, right? And there is something called hidden layer where we have so many interconnected neurons. So each circle is a neuron, which is a cell for, of course, our machines, right? They are all are interconnected. This is connected with this. So every cell is connected, internally connected with each other, and this is how through the hidden layer, right, the information is being passed, and finally with some mathematics, with some formula, right, the output will be generated, and it will be received. Let's see the types of generative models. So first thing is, we understand now that to train the models we need large data set so that we can train the models. Or there are different type of generative models. In this video I have covered 4, but there are many. These 4 are popular, that's why I have covered them. First one is GAN, which is Generative Adversarial Networks, GAN. Variational Autoencoders, VAEs, diffusion models, LLMs, large language models, and there are others as well. Let's see each of them one by one. So first one is Generative Adversarial Networks, GANs. Okay, consider GANs as a friendly competition between two characters. So this is one guy, this is another guy, and this one guy name is generator, another person name is discriminator. Okay, so generator, who will create, generate, we can relate it, who generate, and discriminator is who always criticize, always find problem with what you have generated. So, and they have a healthy fight, of course, a friendly competition, so that based on their fight, of course, one will win over other, and then with that the other one will learn that what were the mistakes earlier, so that I can improve another time. GANs are a class of generative models designed to create new data samples that resemble a given training data set. Okay, two neural networks known as the generator and the discriminator are trained simultaneously through adversarial process, right? This concept, adversarial process, means they are always against each other, simply. Okay, two neural networks known as the generator and the discriminator are trained simultaneously through adversarial process. Generator produces data samples that are close to real data, so it will try to mimic the same data, the real data, while the discriminator tries to differentiate between real and generated data. So for example, first generator will create the data, and this guy, discriminator, right, he say, no man, see, I can see this is not the same. In this one I can see there is a dot, extra dot, right? So just an example. So it will always try to criticize what generator has produced, and generator will try his bestest to produce exact same data, so that discriminate will not be able to distinguish between the real data or the generated data. Okay, let's see the GAN components. And like I said, generator and discriminator are the components. Generator's job is to create synthetic data samples from random noise. We'll see what is random noise. The aim is to generate data that closely resembles the real data in the training set and takes in random noise, latent factor. We'll see all these terms, and generates data samples So for example, images and text, and so it is like this. I have just tried to present it in pictorial format so that pictures, right, our brain is works such a way that we understand pictures and then easy to memorize. Okay, so for example, this is the real data which is already predefined, pre-filled to using our large data set. It is already trained, our model understand it, it's already trained data, and this is how the generator generated this data. But you see there is a slight difference. Although generator tries its best, but there will always be some difference between the real data and the generated data. Discriminator. The discriminator's role is to classify data as either real from the training set, means the data is coming from the training set which is already fed in, or fake, generated by the generator. So real data which is coming from the training set, fake data which generator has just generated. It will just to try to classify. Takes in data sample either real or generated and outputs a probability score indicating whether the sample is real or fake. So for example, this is real, this is fake, right? Actual training data, real sample. So discriminator will see, okay, this is exactly same, so it's real data, so it's classified as real, and this is generated by generator and it's fake, so it will just classify as fake. Now what is the training process? From generator point of view, generator receives random noise as input and transforms it into synthetic data samples. Okay, we'll see what is random noise. The quality of these samples is evaluated by the discriminator. First, generator will generate data using some random noise, and then quality will be evaluated by discriminator. The generator learns to improve its outputs based on the feedback received from discriminator. Simple. Now let's see from the discriminator's point of view. The discriminator is trained on a data set consisting of both real data sample and fake sample generated by the generator. Its task is to maximize its ability to correctly classify the samples, real versus fake. And what is adversarial training? We saw this term that this whole thing works in an adversarial manner. So discriminator and generator are trained simultaneously in adversarial manner. Okay, so they are against each other, right? Because that is how they have been trained, so that they both can improve. While the generator attempts to improve its ability to create realistic samples, the discriminator strives to become better at detecting fake samples. And this adversarial setup helps both networks improve over time. Let's see the fun example. Imagine Detective Dana, who is training to become the best investigator. Dana is learning to solve cases by looking at various clues and evidence. Mastermind Max is a mischievous genius who creates complex and deceptive puzzles to test Dana. For instance, Max might design a case with misleading evidence or hidden clues that require Dana to think outside the box. Now Detective Dana uses Max's tricky puzzles to improve investigation skills. Each time Dana solves a challenging case, her skills get sharper and more refined. Mastermind Max adjusts the complexity of puzzles based on Dana's growing abilities, making sure the challenges remain tough but solvable. So we see, I mean, how these two things are working in adversarial environment, but they are improving others' skills. Okay, let's see this term called a loss function. What is loss function? Generator's loss decreases. Okay, generator's loss decreases when it successfully generates convincing fake data. Discriminator's loss decreases when it accurately classifies real versus fake data. So means loss should decrease, right? So generator's loss will decrease when it will generate such data which discriminate cannot classify as fake. So that's why it's written that successfully generate convincing, which can be convinced that it's real data, but that is fake, right? And discriminator's loss will decrease when it accurately classifies, okay, this is real and this is fake. It means when they both are, as they are improving, their loss is decreasing. As simple as that. Okay, and this term, what is random noise? Random noise is used to introduce variability and diversity in the output. So we want to see different outputs, right? So we want to see different variation. So we add a random noise to the input so that we will get different outputs. Let's see the example. Think of random noise as mixing different colors of paint without knowing exactly how they will blend. Each mix, and mix is nothing but the noise vector, result in a unique shade or pattern, right? So we are just mixing random colors, and then each mix, which is a noise vector, will result in a unique shade or pattern. Imagine adding random or blemishes or spots to an image. Each new blemish pattern result in a different version of the original image. You see this? I mean, these are just example of random noise, right? What is a noise vector? A noise vector is a numerical vector containing random values that serve as the input to a generative model. It is used to generate diverse output from the model. Let's see the example. Suppose we are using a GAN to generate images of handwritten digits. Create a noise vector with 100 random values drawn from a distribution. So we will just provide some random values, some numeric values, right? And there is a very complex mathematics behind, but let's not go into that in detail. It's just we are giving some noise vector. These are called noise vector. Some random values we are giving, right? And with this information, feed this noise vector into GAN's generator. So GAN will take these numeric values. So for example, and it's not actually that way, but I'm just trying to make it more sensible. I have a digit 5. So first, and I'm just multiplying. So 5 into 0.12, I will get one data. 5 into minus 0.45, I will get another data, right? So this is just I'm explaining in very simple language, but yeah, with this distribution, this noise vector, GAN generator will use this noise vector, and then the generator processes this noise vector and produce an image of a handwritten digit such as the number of 5. So in nutshell, noise vectors are just random values which are numeric values. Okay, let's see a fun example. Imagine you are at a cupcake bakery where baker Alex is using a mystery box approach to create a new cupcake flavors, and let's see how it will work. So we are at the cupcake bakery shop, and Alex is having some mystery box. Let's see. Creating the noise vector. Baker Alex has a mystery box filled with various cupcake ingredients like different types of frosting, fillings, toppings, and spices. Each time Alex creates a new cupcake flavor, they randomly select a set of ingredients from the box. You see this, we are selecting randomly. Likewise, we have the noise vector, that is 0, 0.5, all those values, right? The numeric digits. This random selection is like a noise vector. And what is happening with this noise vector? We are getting different final outcomes, different flavors we are getting, right? So an unpredictable combination that influences the final flavor. Let's see where the GAN model can be applied, on which applications. GANs can generate high quality realistic images from random noise or from conditional inputs. GANs can convert images from one domain to another. For example, turning sketches into detailed images, day images to night images. GANs can generate images based on textual description. allowing for the creation of visual content from natural language input. So for example, you will input something, dog is eating something, and maybe that image doesn't even exist, it will create that image. So basically text to image. Let's see the fun example. And guys, I am explaining through fun examples because likewise if it is not interesting, then it will be very boring, right? So I thought I will add more fun examples to the video so that it will be more interactive. Okay, imagine a film studio where a director and a critic are working together to produce a hit movie. I'm not sure if it really happens that director is working with critic, because it always happens when the movie is launched, movie is already released. After that, the critics start coming and then giving the ratings, etc. But let's imagine the director, which is a generator, right? It generates the movie. The director is responsible for creating new movie scenes. They start with the basic script or idea and use their creativity to direct and film these scenes. The goal is to make these scenes look as realistic and engaging as possible. Now the critic, which is a discriminator, the critic watches each new scene created by the director. They are an expert in film and have seen countless movies. I wonder how they must have watched countless movies, of course. Their job is to determine whether the new scenes are as high quality and convincing as seen from top rated films or not. You see this, the adversarial feedback, that environment, that is the whole filmmaking process. Each time the director finishes a scene, the critic reviews it and provides feedback. If the scene is too unrealistic or doesn't meet high standards, the critic points out the flaws and suggests improvements. The improvement loop. The director takes the critic's feedback seriously and makes adjustments to the scenes. Over time, the director learns from the critic's comments and starts creating scenes that are more polished and engaging. The critic in turn becomes more discerning and can identify even finer details. And the final film, after many iterations, of course, of creating and cutting scenes, the director produces a movie that is so well crafted that it is indistinguishable from a blockbuster hit. The critic is impressed by how realistic and engaging the scenes are. So one model is complete, the GAN is complete. Now let's see the another model, which is VAEs, or Variational Autoencoders. VAEs, okay, so designed to generate new data samples that are similar to given training data set. Use an encoder decoder structure. So there in GAN also we have the same encoder and decoder, right? Here also we use an encoder decoder structure to learn a latent representation of data. We will see what is this latent representation. We will see that. Generate new data by sampling from the latent space. Don't worry, we will see what is latent space as well, and decoding it back into the original data space. Now let's see the components used in VAEs. We have encoder, we have decoder, and we have the latent space. Before we go further, let's first understand the latent space. Okay, the term latent means undiscovered, which is not yet discovered. Okay, and another dictionary word says something that exists but is not yet visible, apparent, or active. So it means no one has seen it. It's just imagination, right? Something imagination. The latent space is a continuous lower dimensional space where the data is represented. Each point in the space corresponds to a possible data sample. Of course, let's see this latent space, right? Okay, let's see it with some fun example. Imagine a cooking show where chefs are creating unique dishes based on a set of ingredients. Okay, so this is the whole set. we have a cooking show. Chefs are there. They are creating unique dishes, and they have ingredients. So chefs are generative models. Okay. Ingredients are basically the raw data. Whatever ingredients we have pepper, vegetables, etc., salt, etc., whatever we need, right? What will happen? Chefs, basically the generative models, using those ingredients will create some and will use the recipe, right? They will use the recipe, and there are different recipes, okay, various recipes. Now they will take one recipe. Using that recipe, they will add different type of ingredients, right? Different type of quantity of each variant, and then finally different dishes will be produced after that, right? So there are various recipes in the recipe book. Okay, the recipes are analogous to the generative models parameters, of course. I mean, they are related to what you are cooking, right? What is there in the recipe. They determine how the ingredients are combined to create different dishes. Just like different recipes can lead to a wide variety of dishes, different model parameters can generate diverse outputs. Okay, so dish is ready. Where is latent space, right? Think of latent space as the recipe book in this cooking show. So remember, this latent space is nothing but that recipe book which is having so many recipes. This recipe book contains an abstract collection of recipes that can generate a wide variety of dishes even if the exact details are not explicitly stated. Each recipe in the book represents a combination of ingredients in a way that results in a specific dish, right? Latent space is a multi-dimensional space where each point represents a possible recipe, and these recipes are not directly visible but can be mapped to a specific dish when the right ingredients are used. So I hope it makes sense now, right, with this example. The chefs can explore different sections of the recipe book to create various types of dishes. They might find a section for spicy dishes, sweet desserts, or savory meals, etc. Each section represents different region in the latent space. Navigating latent space involves moving through different regions of this abstract recipe book. For instance, adjusting the recipe slightly might result in a spicier or sweeter version of the dish, similar to how changing the parameters in the latent space might alter the generated outputs. So we are just trying to map that there are those different ingredients. Those different ingredients are the raw data, and the different mapping of these ingredients. I mean, how you are mixing those ingredients. You are taking one chili and then maybe half kg potato, or next time you are taking 1 kg potato and mixing it with something else. So how much raw data you are taking and which recipe you have selected, on basis of that you are getting various outputs. That is the whole concept behind. Okay, the next concept is VAEs encoder. So we know the components are encoder. VAEs components are encoders, decoders, and latent space. So what is latent space? Let's see encoder. The encoder maps the input data to a latent space representation. Okay, so we have the latent space where lots of recipes are there. What is encoder's job? It will map the input data. Whatever is the input data, it will map to the latent space. It learns to compress the input data into smaller continuous representation. The encoder produces two outputs, okay, the mean and the variance of the latent space distribution for each data sample. It will go little bit mathematical, but in this tutorial I just kept it theoretical, since it's a multi-dimensional and low dimensional space which is called a latent space, and these dots right? Because we map the data, input data, to somewhere in the latent space, right? So consider it's a room where so many dots are there, right? And whenever we'll get the input, we'll just try to map it against one of the input, one of that dot, right? Now that dot is having is kind of this place where you want to map it against your input data. Now encoder first will map it to that dot with the input data, that is one thing, and then encoder produces two outputs, the mean and the variance of the latent space distribution for each data sample. Decoder takes points from the latent space and reconstructs the original data from them. It learns to generate data samples that resembles the input data. The decoder generates data samples by mapping latent space representations back to the data space. Okay, VAEs, variational inference. What is this term? Let's understand. Okay, VAEs, it is used to approximate the true posterior distribution of the latent variable given the data, and it provides a tractable way to estimate the distribution. VAEs use a variational distribution, approximating distribution. Okay, that's why it's called variational distribution, to estimate the true posterior, and the goal is to minimize the difference between these distributions. So let's see this, how VAEs work. So first one is encoding. The encoder network takes an input data sample and maps it to the mean and variance of the latent space distribution. So like I said now, just consider latent space, it's kind of a recipe book or a room, right? There are so many recipes are there, or if you are thinking of it as a room, that just consider a point within a room, right? What encoder will do? Encoder network takes an input data and then map it against mean and variance of the latent space, mean and variance. So for example, if you have already, you must have read, right, this XYZ whenever we work in the 3D dimensional work area. So consider if this input point is having XYZ notation, so just consider that. So it will just map it. Now after encoder sampling, from the distribution defined by mean and variance, a latent variable is sampled. This is done using the reparameterization trick. We'll see that, which allows for back propagation through the sampling process. We will see these terms, what is back propagation, etc. Then decoding, the latent variable is fed into the decoder, okay, that latent variable which we have received, which generates a reconstruction of the original data sample. We see that we first use encoder. What encoder does? Encoder network takes an input data sample and then maps it to the mean and variance of latent space, and decoder, latent variable is fed into the decoder, right, which generates a reconstruction of the original data sample. And latent variable is nothing but the mean and variance. Okay, loss function. What is loss function here? So there are types of loss functions. Reconstruction loss is first one. It measures how well the decoder reconstructs the input data from the latent representation. This is typically computed using a loss function such as, and let's not go in detail of these terminologies, but yeah. So basically reconstruction loss is measures how well the decoder reconstructs the input data from the latent representation. The second one is this loss, KL divergence loss. It measures the difference between the learned latent space distribution and a prior distribution. Okay, and the goal is to keep the latent space distribution closer to the prior. And the overall loss function is a combination of the reconstruction loss and the KL divergence loss. And in a nutshell, what we need to understand is we are using encoder, we are using decoder. Encoder is getting the input data, mapping it to the latent space means and variance, right? And the decoder, it is getting data from the latent space, trying to convert it to reconstruct the original data, right? And in between of these, right, when this encoding or decoding is happening, some loss is happening. How we calculate this loss? Using two methods. One is the reconstruction loss, one is the KL divergence loss. Overall loss is the combination of these two loss. That is the overall summary. Okay, what are the applications where we can use VAEs models? Image generation. VAEs can generate new images by sampling from the latent space and decoding these samples. This is used in creating synthetic images and image interpolation. Anomaly detection. By learning a compact latent representation of normal data, VAEs can identify anomalies or outliers that deviate from this learned representation. Okay, let's see the fun example of VAEs. Imagine you have a magical closet that can take all your existing clothes like shirt, pant, trousers, shoes, and use them to design new outfits. I am not sure if such type of magical closet exists. So all those merchandising outlets, they will be closed. Okay. So we have a magical closet, and which will take all your existing clothes. That is the idea. Closet inventory, which is encoding. First, you put all your clothes into the closet. The magical closet analyzes each piece, learning about patterns, styles, and combination from your entire wardrobe. The design ideas, which is a latent space. So this one is encoding. Okay, this is latent space. Inside the closet, there is a secret room called the latent space. Now this room stores abstract representations of all your clothes, like the essence of different styles and patterns. For example, it understands that a particular shirt and trouser combination is casual while another is more formal, right? So that we have. Now output creation, which is a decoding. So we have fitted the data and we have the latent space. Now we are decoding, means we are trying to get something new. When you want a new outfit, you tell the closet your preferences, like give me casual colorful shirt or something like that, right? Casual and colorful. The closet uses the latent space because this information is there, right? The closet uses the latent space to mix and match different abstract concepts, then creates a brand new outfit that combines elements from your existing clothes in unique ways. And the variations we'll see, because the closet can remix and match in creative ways, it might come up with unexpected stylish combinations that you had not thought of before. It is like getting a new wardrobe every time you ask for a fresh outfit. So you see this, I mean, how it is, it makes sense, everything now, encoding, decoding, sampling, and this loss function, etc., how it is happening. Okay, so these are also done. Now let's see the next model, which is diffusion model. Okay, diffusion model generate data by simulating a process where data is progressively noised and then learning to reverse this process. So first noise will be added and then learning to reverse the process. And okay, and it has gained significant attention for their ability to generate high quality data, particularly images. And diffusion models can be used to generate detailed images from noisy data. That is one of the applications. Okay, let's see the components of diffusion models. So we have forward diffusion process, reverse diffusion process, and we have loss function. So first we do the data preparation, which is forward diffusion process. This process is usually modeled as a stochastic process where noise is added at each step. The forward diffusion process gradually adds noise to the data until it becomes pure noise. So for example, there is an image, you will add noise to it. We'll keep on adding noise until it becomes pure noisy. It is not even distinguishable. It is not visible at all. Then learning to denoise, which is the reverse diffusion process. The reverse diffusion process aims to reconstruct the original data from the noisy data by learning to denoise it step by step. This involves learning how to reverse the noising process. The model is trained to reverse the noising process and generate realistic data samples. So first we add the noise until it becomes pure 100% noisy, and then we reverse it to reconstruct the original data. Okay, let's see the sampling process. Start with pure noise and apply the learned reverse process to generate new samples. The model iteratively refines the noisy input to produce samples that resembles the training data, means original data. Okay, let's see the loss function in this model. The loss function measures the discrepancy between the predicted and actual noise or data at each step. Commonly used loss include mean square error or variational lower bounds. Okay, let's see how do we train the diffusion model. The objective of training a diffusion model is to learn the reverse process parameters such that the generated samples from the noise resemble the original data distribution. This is often done by minimizing a loss function that measures the difference between the generated and the original data distributions. Okay, let's see the applications where it can be used. For generating high quality images by learning to reverse the diffusion process from noise to data. By manipulating the latent space or intermediate steps of the diffusion process, diffusion models can be used for image editing such as in painting, super resolution, style transfer, etc. Okay, models can be extended to generate images based on textual descriptions by conditioning the diffusion process on text embeddings. Okay, let's see a fun example of diffusion models. Imagine you have a magical puzzle that starts with a jumbled mess of pieces and slowly transforms into a complete picture. Likewise, we used to play in our childhood that we need to arrange the pictures, right? That one. You begin with a scrambled set of puzzle pieces where each piece is just a random shape with no recognizable patterns, like a chaotic splatter of colors. This represents the initial noise in the diffusion model. So you kind of have different pieces. Those pieces are of different shapes, but now you need to arrange them, kind of that. Your magical puzzle solver starts by carefully placing and connecting pieces that seem to fit together. With each step, the solver refines the arrangement, making sure pieces are getting closer to their correct positions. At this stage, the image starts to slowly take shape, though it is still not clear what is supposed to be. Now, detailed refinement, image enhancement. As the process continues, the solver adds finer details and corrects mismatches. Each piece is adjusted with precision, enhancing the clarity and coherence of the image. The puzzle begins to look more like a recognizable picture, perhaps a beautiful landscape or a vibrant cityscape. The final masterpiece, which is the completed image, after many careful adjustments and refinements, the jumbled puzzle pieces are transformed into a stunning, complete image. What started as random noise is now a clear and detailed picture ready to be admired. Now let's see the next model, which is large language models or LLMs. Large language models are designed to understand, generate and manipulate human language, trained on vast amounts of text data to perform various language related tasks including text generation, translation, summarization and more. And you know what? The famous Chat GPT, right? It originally used the GPT-3 large language model only. Uh, okay, so let's go on. Okay, generative capabilities. LLM can generate coherent and contextually relevant text based on input prompts. So we provide prompts, and then on basis of prompts, the response will be given, right? And remember one thing: these are already fed with lots of data, and with that pre-trained information only, the model will respond to the prompts. Then let's see the training process of LLM. LLMs are typically pre-trained on large corpora, large data in GBs, even more than GBs of text data using unsupervised learning technique. We already seen what is unsupervised learning. During this phase, they learn the statistical patterns and structures of language. After pre-training, LLMs can be fine-tuned on specific dataset to adapt them to particular tasks or domains such as medical terminology or customer support. So what does that mean? So for example, we can fine-tune our model. So for example, if I try to ask something related to Tech Talk with Ritesh from ChatGPT, right? It won't be able to answer because maybe it is not having that much information about the account, my personal details, etc., right? And if I want to train my model for anything which is specific to my organization, uh, uh, my specific data information, right, or any organization internal organization specific information, something related to medical healthcare, etc., right, then it can be fine tuned. What we need to do, we need to pre-train that data. We need to train the model with specific data set. We need to feed in those documents, right, to our models. That then only it will be trained. Then only uh, uh, it will know that okay, what are the keywords a prompt can we can use in the prompt, etc., right? So after pre-training of LLMs, it can be fine-tuned on specific dataset to adapt them to a particular tasks or domains. Okay, let's see the architecture of LLM. LLMs often use transformer-based architectures, which are highly effective for capturing long-range dependencies and context in text. Transformers use mechanisms like self-attention to process and generate text. Let's see the applications where we can use LLM. Conversational AI, building chatbots and virtual assistants that can engage in meaningful dialogues with users. Content creation, generating articles, blog, post, and creative writing, right? Translation and summarization, translating text between languages and summarizing lengthy documents. Okay, let's see a fun example of LLM. Imagine you have a high-tech robot named Roboteller that is fantastic at telling stories. The library of knowledge, okay, which is our training data. Roboteller has read an enormous library of books, articles, and scripts. You have fed that data, so many documents you have given to the Roboteller. That's why it's no. That's why this robot, he knows that what is the answer of this question or of that prompt. This vast collection of knowledge includes everything from fairy tales to scientific articles. Think of it as having an encyclopedic memory of countless stories and facts. Now input, which is our prompt. You decided to have some fun with Roboteller. You give it a prompt like, tell me a story about a dragon who learns to dance. Now this is like giving Roboteller the starting point for a new story. The creative process, which is generating the text. Using its extensive knowledge, Roboteller begins to weave a story. It considers different elements from its library, such as dragon lore, dancing, and storytelling techniques. So, I mean, this data is already there to create a unique and engaging narrative. Now, story unfolds, the output finally what it generates, right? Within moments, RoboTeller delivers a delightful and imaginative story about a dragon named Spark, who, despite being clumsy at first, learns to dance gracefully and impresses everyone in the enchanted forest. The story is coherent, engaging, and often includes surprising twist and new. Like I said earlier, new. It's new data. Endless possibilities, customization. You can keep playing with RoboTeller by changing the prompts. We just need to change the prompt. Want a mystery about a detective squirrel or a science fiction adventure with space faring cats, etc. Just provide a new prompt and RoboTeller will spin another fantastic tale based on its vast knowledge. And prompt is basically, so for example, if you use ChatGPT, you put something in that text field and hit an enter, that is prompt. Basically, you ask some query, you ask some suggestion, whatever you ask, that is a prompt. Okay, let's see the summary of LLM. Large language models are indeed a part of generative AI. They exemplify the use of generative technique to produce human-like text, leveraging extensive training data and advanced architectures like transformers. They are widely used in applications that require natural language understanding and generation, demonstrating the power of and versatility of generative models in the field of AI. So far, what we have learned is what are the models in Gen AI, the popular models, and we have learned about them. What is the training, how they are being trained, how they are being used, in which applications they can be used, etc. Now let's see the overall applications of generative AI. So these are the applications, for example, art and design. Generative AI can produce original artwork, designs, and creative content such as paintings, fashion designs, etc. In entertainment also we can use. In video games and virtual world, generative models can create new levels, characters, and scenarios. In text generation we can use human-like text for chatbots, content creation, language translation, etc. What are the challenges in generative AI? Let's see. Quality control, ensuring that the generated content is of high quality and useful for its intended purpose. Ethical concerns, addressing potential misuse of generative models, such as creating deep fakes or generating misleading information. Sometimes ChatGPT, for example, or generated data, we should always check if it is, and maybe sometimes we get some information which we believe it's real. We should always check the authenticity of that information which we receive. So that's why it's ethical concern. Okay, computational resources. Training generative models often requires substantial computational power and resources. Nowadays, actually, this is not a problem because we have now great CPUs, etc., GPU, etc. we have, so that is not a problem anymore by any way. Now we have already covered GANs. Let's see a few variants which are popular, with a few variants of GAN. Okay, GANs have inspired a variety of modifications and extensions, each designed to address specific challenges or improve performance in certain tasks. Let's see a few examples. Vanilla GAN, and like I said, there are many, but I just put few of them. I checked like which are popular, and I just put only the popular ones. So Vanilla GAN or Original GAN. Original GAN framework introduced by this person, consisting of a generator and a discriminator that we know, that compete in an adversarial setting to produce realistic data samples. Then we have DC GAN, enhance image generation by using deep convolutional networks in both the generator and discriminator, leading to improve image quality and stability. Then we have CGAN, Conditional GAN, extend GAN by conditioning the generation process on additional information. So for example, labels, allowing for controlled and specific data generation. We have StyleGAN, facilitates unpaired image to image translation, enabling transformations between two image domains without requiring paired examples for training. We have Pix2Pix, designed for paired image to image translation tasks, and it maps images from one domain to another using corresponding paired datasets. Then we have WGAN, introduces the was a strain distance as the loss function to improve the stability of GAN training and address issues like mode collapse. Then we have progressive growing GAN, uses a progressive training approach that gradually increase image resolution, leading to high resolution and photorealistic images. StyleGAN generates high quality images with advanced control over styles and features, allowing for high realistic image synthesis and manipulation. And the next concept is data augmentation. Augmentation. What is augmentation? Augmentation is the process of increasing the size, value or quality of something by adding to it. Okay, that is called augmentation. So data augmentation is we are going to add some data, more data to it, right? That is data augmentation. Okay, the data augmentation is a technique used to artificially increase the size and diversity of training data sets by applying various transformations and modifications. A process of creating new training samples by applying transformations to existing data. And we need more data because we want to train our model. So that's why we need more training data. How do we get more training data? We create more samples, more training samples. And how do we create more training samples? By adding some diversity, some size, increase the size, and that is called data augmentation. Let's see the purpose of data augmentation. Increase data set size. Like I said, by generating additional variations of the existing data, data augmentation effectively increases the size of the training data set without the need to collect more real world data. So we have some data, we want to increase the data size, we use data augmentation to increase the data set size. Improve model generalization. Augmented data introduces variability that helps the model generalize better to different scenarios, reducing overfitting and improving its ability to handle unseen data. We'll see what is overfitting, right? But we just want to improve the model generalization. Enhance model robustness. Data augmentation can make the model more resilient to variations and perturbations in the data, leading to better performance in real world applications. Now let's see the common data augmentation techniques. First one is image augmentation, and if we use the smartphone, right, we actually do it regularly with our images. Okay, rotating images by a certain angle to simulate different viewpoints. Scaling, resizing images to simulate different zoom levels. Cropping, extracting random regions from images. So for example, I have an image, I am there inside that image, but there are so many people also, but I just want my image. I'll just zoom it, crop my image and get the image. Color jittering, adjusting brightness, contrast, saturation and hue. Noise addition, adding random noise to images to improve robustness. Next is text augmentation. Okay, this one, synonym replacement, replacing words with synonyms to create variations. That's amazing, right? So we have a word, we just create another one with synonym. Random insertion, inserting random words or phrases. Text shuffling, rearranging sentences or words within the text. Back translation, translating text to another language and then back to the original language to generate paraphrased versions. Next one is audio augmentation. For example, pitch shifting, changing the pitch of audio recordings, time stretching, altering the speed of audio without changing its pitch, noise injection, adding background noise to audio samples, volume adjustment, changing the volume levels of audio recordings. You see this how interactive it is. We are just talking about data augmentation only, and which is to train our model, and we need more data set, and this is how we are getting more data samples. Let's see this data augmentation in generative models. Enhancing training data for generative models like GANs and VAEs by applying augmentations to real data. These models learn to generate more diverse and realistic samples. Integrating into the training pipeline of generative models to ensure that they are exposed to a broader range of data variations. Let's see some of the challenges and considerations of data augmentation. The choice of augmentation techniques should be relevant to the specific application and data type. Inappropriate augmentations may lead to unrealistic or irrelevant data variations. Generating augmented data can introduce additional computational overhead, especially for large datasets or complex transformations. It's important to balance the use of augmented data with original data to ensure that model benefits from both real and augmented examples. It should not be like you have created so much augmented data and the real data is very less, and augmented data is not even matching with the real data, and your model is trained on wrong data. Let's see this terminology called inception score. Inception score is a metric used to evaluate the quality of images generated by generative models. It provides a quantitative measure of both the diversity and quality of generated images. It measures how well the generated images match real image in terms of both the clarity, quality and the variety of the image. Let's see how do we interpret inception score. High score. A high inception score indicates that the generated images are both high quality and diverse. So it means we need high score. It means that each image is confidently classified into a specific category, high confidence, and the set of generated images covers a wide range of different categories. If it is a low score, a low inception score suggests that the generated images either lack diversity or are of poor quality. For example, if the images are poorly generated, the inception network may be unsure about their classifications, leading to a low score. Alternatively, if all images are similar and belong to only a few categories, the score may also be low due to insufficient diversity. Let's see the example calculation of inception score. Suppose you have a generative model that produces images of cats and dogs. After generating a set of images, you pass them through a pre-trained inception network. The network provides probability distributions for each image over categories like cat, dog and others. For high quality and diverse images, the inception network should confidently classify each image into a specific category, high conditional probability, and cover various categories in the generated set, that is high diversity. If the images are all similar or of poor quality, the network might give uncertain classifications, which is actually a low conditional probability, leading to a lower inception score. Now let's see all the key terminologies we have used so far in this session, okay, which are related to generative AI. So start with the very basics. Generative AI, a branch of artificial intelligence focused on creating new data samples that mimic the distribution of given data set. That is generative. Generative models, models that learn to generate new data instances by understanding the underlying distribution of a training data set, they can create new samples that are similar to the ones in the training set. Then GAN, Generative Adversarial Networks, a type of generative model comprising two neural networks, the generator and the discriminator, that are trained simultaneously in a competitive setting. The generator creates data while the discriminator evaluates its authenticity. Generator network. In GANs, the generator network is responsible for creating new data samples that mimic the training data distribution. Discriminator network. In GANs, the discriminator network evaluates the authenticity of the data samples produced by the generator, aiming to distinguish between real and generated data. Then we have VAEs, Variational Autoencoders, a type of generative model that learns to encode data into a latent space and then decode it to reconstruct the original data, while also generating new data samples by sampling from the latent space. Then we have latent space, a compressed representation of data learned by generative models. It captures the essential features of the data in a lower dimensional space, allowing for the generation of new data samples. Then we have autoencoder, a neural network architecture used for encoding data into a compressed representation and then decoding it back to reconstruct the original data. It is used in VAEs to learn data representation. Then we have loss function, a mathematical function used to measure how well a generative model performs. It quantifies the difference between the generated data and the real data, guiding the model's training process. Then we have training data, the data set used to train generative models. It provides examples from which the model learns the underlying patterns and structures. Overfitting, when a generative model learns to produce data that is too similar to the training data, failing to generalize well to new unseen data, that is overfitting. Underfitting, when a generative model fails to capture the underlying distribution of the training data, resulting in poor performance in generating new samples, that is underfitting. Then we have epoch, one complete pass through the entire training dataset during the training process of a generative model. If a GAN is trained for 50 epochs, it means the model has gone through the training data 50 times. Then batch size, the number of data samples processed in one iteration of model training. A batch size of 64 means 64 images are processed before updating the model's weights. Gradient descent, an optimization algorithm used to minimize the loss function by iteratively updating model parameters in the direction that reduces the loss. Backpropagation, a method for computing the gradient of the loss function with respect to each weight in a neural network, enabling the model to learn and adjust weights during training. Backpropagation is used in GANs to update the generator and discriminator networks based on the computed gradients. Overparameterization, when a generative model has more parameters than necessary, potentially leading to overfitting or computational inefficiencies. A GAN with too many layers might become overparameterized and struggle with stable training. Regularization, techniques used to prevent overfitting in generative models by adding constraints or penalties to the loss function. Regularization methods like dropout or weight decay can be applied to VAEs to reduce overfitting. Noise injection, adding random noise to the input or hidden layers of a generative model to improve robustness and generalization. Injecting noise into the training data of a GAN can help the generator create more diverse and realistic samples. Mode collapse. A problem in GANs where the generator produces a limited variety of outputs, failing to capture the full diversity of the training data. A GAN might generate only a few types of images rather than a wide range of diverse images. Transfer learning. Using a pre-trained generative model as a starting point to improve performance on a new related task. A GAN trained on general images can be fine-tuned to generate specific type of art or design. Reinforcement learning. A learning paradigm where an agent learns to make decisions by receiving rewards or penalties based on its actions. Reinforcement learning can be used to optimize the performance of generative models by rewarding good samples and penalizing poor ones. Attention mechanism, a technique used in neural networks to focus on specific parts of the input data when generating or processing information. Example, attention mechanism enhance models in tasks like machine translation by focusing on relevant words or phrases. Self-supervised learning, a learning paradigm where the model generates supervisory signals from the input data, except often used in training generative models. VAEs use self-supervised learning to reconstruct data and learn useful representations. Text to image generation, the process of generating images from textual descriptions using generative models. Models like DALL-E can create detailed images from textual prompts like a futuristic city skyline at sunset. Image to image translation, converting an image from one domain to another, such as transforming sketches into detailed color images. StyleGAN can translate between different image styles like turning daytime photos into nighttime scenes. Style transfer, applying the visual style of one image to the content of another image using generative models. Neural style transfer can apply the style of famous artists to personal photographs. Then we have data augmentation, techniques to artificially increase the size and diversity of a dataset by creating modified versions of existing data samples. Generative models can augment image datasets by creating new variations of existing images. Zero-shot learning, a learning paradigm where a model can recognize or generate data for classes or tasks it has never seen before. A generative model trained on a limited set of animal images can generate images of new animals it has never encountered. Then unsupervised learning, a type of machine learning where the model learns patterns and structures from data without explicit labels or annotations. VAEs use unsupervised learning to generate new samples by discovering hidden structures in the data. Then we have supervised learning, a type of machine learning where the model is trained on labeled data to predict or classify new data based on these labels. In GANs, supervised learnings can be applied to the discriminator network to learn to differentiate between real and generated samples. Then we have conditional generation, generating data samples based on specific conditions or inputs provided to the generative model. And for example, conditional GANs generate images based on labels, such as generating images of different breeds of dogs given the breed label. Okay, and that wraps up this session. Thank you so much for joining me on this journey. I hope you found this information as fascinating and inspiring as I do. If you enjoyed this video and learned something new, please hit that like button and subscribe to the channel. Your support means a lot, and of course it will help me create more content like this. If you have any question or topics you would like me to cover in future videos, drop them in the comment section. I would love to hear from you. Stay tuned for more deep dives into cutting edge technologies and for exciting tutorials right here on Tech Talk with Ritesh. Until next time, keep exploring, stay curious. Thanks again for watching, and I will see you in the next video. Take care and have a great day.